Hi guys! In this video, we're going to be talking about Gauss's theorem. This will help us evaluate surface integrals of vector fields across closed surfaces. Now, without further ado, let's begin. In the previous lectures, we found out that if we are given a vector field f and a surface S which is parameterized by r, we can find the surface integral of f across S by evaluating the double integral given as follows. On the other hand, if it has a Cartesian equation z equal to g of xy, we have a corresponding double integral that evaluates it. This solves a lot of our surface integrals, but one of the main drawbacks will be, one, we need to be able to parameterize our surface, or it should have a Cartesian equation. And another one will be if my vector field f, my parameterization r, or the partials of my function g of xy will be complicated, then the integrand on the right hand side will also be complicated and possibly will not be able to evaluate it. For example, if you consider the following vector field f of x, y, z on the unit sphere, clearly if we evaluate the coordinate of the parameterization on f, it will have a very complicated quantity and thus will inhibit us in evaluating our problem or our integral. Now it's good to note that the sphere that is given in this example is closed. In cases such as this, we can use a technique which will be the main topic for today, and that is called Gauss's theorem. This theorem states that if I have a closed and bounded solid, and S to be its surface boundary which is piecewise smooth, F being a vector field whose components have continuous first partial derivatives, and last but not the least, N be the outward normal vector, then the surface integral of f across our surface S will be given by the triple integral of the divergence of f over our solid G. This theorem connects two types of integrals. The first one is a surface integral, which gives us a flux, while the other one is a triple integral which we studied when we were studying volumes. This type of technique helps us broaden the methods that we can use in evaluating our surface integrals, because instead of using the definition we have learned in the previous slide, we're going to be evaluating it using a triple integral, and that is we will use our different coordinate systems, namely the rectangular, cylindrical, and spherical coordinate systems, to evaluate and set up our triple integral. Unfortunately, for us to be able to use Gauss's theorem, our surface should be closed because it should enclose a solid. And this is in particular to our notation where we used a loop with our surface integral that indicates that the surface that we are dealing with is closed. Now, Gauss's theorem is a very powerful theorem, as not only does it give us another method in finding the flux. In general, what it means is that even though to study a triple integral, we need to evaluate the divergence of f at every single point. The Gauss's theorem states that the integral of the divergence of f is completely determined by the values of f dot n across its surface boundary, where it means the whole of the solid is studied by just studying its boundary. Now, it's very unfortunate that we will not be able to prove this, but we are going to be giving examples for Gauss's theorem. To aid us in memorizing this theorem, I'm going to be placing this theorem on the left side of the screen. Now let us have our first example. Suppose I have the function f 0, 0, z cubed, and the unit sphere S. We wish to find the surface integral of f dot n over S, where n is the outward unit normal. We want to do this in two ways. First one will be using the definition, and also we will be using Gauss's theorem. Let us first use definition. To use definition, we will need to either parameterize my surface S, or we will need to find a Cartesian equation that describes our S. Unfortunately, we cannot find a Cartesian equation z equal to g of xy that will describe fully our sphere. So we will be parameterizing this using what we learned in spherical coordinate system. And that is, if we take rho to be equal to 1, the parameterization of the sphere will be given by sine phi cos theta, sine phi sin theta, and cosine phi, which are exactly the coordinates of x, y, and z with rho equal to 1. Of course, phi here will still run from 0 to pi, and theta will run from 0 to 2 pi. To evaluate this, we will need to first find the cross product of r with respect to phi and r with respect to theta, given as follows. And thus, by definition, the flux will be given by the following. Evaluating my vector field F on the coordinate given by the parameterization r phi theta, getting its dot product with the cross product we obtained before. Phi here will be from 0 to pi, and theta will be from 0 to 2 pi. Since my vector field F is just 0, 0, z cubed, then if I evaluate the x, y, z values here, I will only have a cosine cube on my third component and 0 on the other two. If I now get the dot product we have here on the one that we have solved before, then the first and the second component will just be zeroed, while the third component will be a cosine to the fourth times the scalar multiple sine phi. And since our integral have constant limits, we can use the method we have learned in the previous lectures, where we can split this iterated integral into two separate integrals, one for theta, which is 0 to 2 pi 1, and the other one will be all for phi, sine phi cosine to the fourth phi. If we evaluate this, the first integral will just be a 2 pi, the second will be a 2/5, giving us a total of 4/5. Now, what about using Gauss's theorem? If I'm going to use Gauss's theorem, I will be applying the formula that we have on the left side of the screen, and that is the flux is equal to the triple integral of the divergence of f. So we first need to find the divergence of f, which is easily obtained to be 3z squared. Now, the main difficulty for using Gauss's theorem is that we need to solve a triple integral, and that is, we need to analyze our solid and know what type of coordinate system I will be using. Since clearly this is a sphere, I will be using spherical coordinates, and that is that the divergence of f over the solid g. I will express this in spherical coordinates. The dv will just be a rho squared sine phi d rho d phi d theta. The limits of my rho will be, since this is a unit sphere, from 0 to 1. Phi will be from 0 to pi, and my theta will be 0 to 2 pi, since I will be studying the whole sphere. Of course, we will also need to convert 3z squared in terms of rho and phi, and that will just be a rho cosine phi squared. Similar to the example before, the limits of my integrals are all constants, and thus I can split this into three integrals. I can factor out the 3, and the first integral will be the integral for theta, 1 from 0 to 2 pi. The integrand for phi will be cosine squared phi sine phi. This will run from 0 to pi. And the integrand for rho will be rho to the fourth from 0 to 1. Evaluating each one and multiplying it, you will obtain exactly the same answer for pi over 5. You will see whatever method that we use, we will obtain the same answer. Now, both of these techniques have their own drawbacks. For one, using the definition requires us to parameterize as well as to find the cross product of the partials of my parameterization, and later on getting its dot product with the evaluation of my vector field. The evaluation itself can become complicated, and that is one of its main drawbacks. On the other hand, Gauss's theorem requires you to get the divergence. And in some cases, the divergence will also become complicated because, as you may know, you are getting derivatives here. But one of the greatest drawbacks of Gauss's theorem will be that you need to evaluate the triple integral, and thus requires that you have mastered on the evaluation using our three main coordinate systems. And last but not the least, one of the greatest weaknesses of Gauss's theorem is that you can only apply this on a closed surface. In this case, if we are only given a hemisphere instead of a sphere, we cannot use Gauss's theorem directly. Now let's have another example. In this, one great application of Gauss's theorem is that what will happen if the divergence becomes a very simple quantity. This is demonstrated by this example here. I want to find the outward flux of the vector field f x, y, z across the surface sphere and the unit cube. Now if you notice, if you use Gauss's theorem here, the flux will become the divergence, the triple integral of the divergence over the solid G. And the divergence is simply 3. If I factor out the 3, I will be left with the triple integral of dv across G or over G, and that will just give me 3 times the volume of G. Since the sphere will have volume 4 pi over 3, then that will tell you that the flux will just be 4 pi. Similarly, if you have the unit cube E, then the flux will be just 3 times the volume of E, and since this is just a cube, that will have a volume of 1, giving you a flux of 3. This will be this is much simpler than using the definition. For one, if I use the definition for the unit sphere, I will need to parameterize it just like before, and it will become much complicated. But the simplicity is much more emphasized for item 2, because the unit cube will have 6 sides. It means to use the definition on the unit cube means that you need to parameterize those 6 sides and then evaluate those 6 integrals, which may not be hard, but definitely it will be much tedious than just using Gauss's theorem. Of course, this is a very special example where the solid that I am dealing with is simple. In case that the solid that I am dealing will be much complicated, of course, even though I am solving for the volume, it won't be as easy as this. So it really proves that there is no such thing as the best technique. It's a case-to-case basis. Sometimes the definition is easier, and sometimes Gauss's theorem will be easier. But true enough, Gauss's theorem shines, especially when the divergence of f becomes simple. And a prime example for this will be our first example, where we wish to find the outward flux of the vector field f given as follows on the unit sphere. The unit sphere is again closed, ergo you can use Gauss's theorem, and thus the flux will be the triple integral of the divergence of f over my solid G, and since the first component of my vector field does not have an x, the second component does not have a y, and the third component does not have a z, the divergence will just be 0, giving me a 0 flux. Actually, in this type of problem, whatever the closed surface I have, it will always be 0, since the components of my vector field will always have continuous first partials. Now we see now that the Gauss's theorem will be very useful, especially if the divergence will be simple. Of course, in general, that is not true. We need to know how to evaluate a triple integral as is demonstrated by our example here. So for example, I wish to find the upward flux of a fluid with the following velocity across the boundary of the cylindrical shell given as follows. It is easy to see that the divergence of F will just be 2z, which is not 0. It's also not constant, and thus we will need to analyze our cylindrical shell. X squared plus y squared here is very similar to the formula for a circle. So in the xy plane, 1 equal to x squared plus y squared is just the circle of radius 1, and equal to 4 is a circle of radius 2. So this is just the area between those two circles, while z running from 0 to 2 means that I will need to translate this donut shape in the xy plane upwards until 2. That is given by this cylindrical shell here. Let me call that G. By Gauss's theorem, flux is equal to the triple integral of your divergence, which is just 2z. As I've said before, we need to evaluate this triple integral. So I'll analyze whether I will be using rectangular, cylindrical, or spherical for this triple integral. Clearly, since this is best in cylindrical coordinate systems, I will use the cylindrical coordinates, noting that the solid G will just be the solid or the collection of points r, theta, z, where r will be from 0 to 2, and we see that because the radius will be from 1 to 2. Theta, because this is a full circle, will be from 0 to 2 pi, and the z will still be from 0 to 2. Thus, the flux will be, in cylindrical coordinates, dv will be r dz dr d theta. The limits of z will be 0 to 2. The limits of r will be 1 to 2, while the limits of theta will be 0 to 2 pi. Of course, 2z in cylindrical coordinates will still be 2z. Similar as before, the limits are all constants, and thus we can again split them into 3 integrals. The first one having an answer of 2 pi, second 3 halves, the third will be a 4, as a total of 12 pi. Now we learned that the Gauss's theorem helps us evaluate flux, and this is through evaluating a triple integral of the divergence of F. Another good application of Gauss's theorem is the understanding of divergence. We have learned divergence earlier in the previous lectures as just nabla dot your vector field F. But as of its physical interpretation, we still have not yet studied it. But because of Gauss's theorem, we can now try to study the physical interpretation of the divergence of a vector field. Let us again recall the Gauss's theorem. This is the equality of a surface integral equal to the triple integral. Because of its equality, we can easily see that if I have a property on the triple integral of the divergence, that will translate to the property on the flux, which will be what we will be doing in our next exercise, which is, suppose I have a point in R3 and S containing this point. I wish to know what happens when the divergence at this point is positive. Now for simplicity, suppose that every point inside this cube will have positive divergence. Since everything will be positive, if I get the triple integral of the divergence of F over this solid G, which is our surface here, over our solid, which is our solid here, it will become positive, and in turn will mean that our flux will be positive as well. Flux being positive mean that the outward orientation of my surfaces will be the same as the direction of my force field, which will look something of this form, since we have assumed that the end here will be pointing outward. Now, what will happen if I have another box, say S1? This is still contained in S, but it will still contain P naught. So it's a smaller box inside S that contains P naught. Now, since every point in S will have positive divergence, S1 being a subset of S, means every single point in S1 will have positive divergence as well, because it is just inside S. That means total flux of F inside of the total flux of F over the surface S of 1 will be positive, and thus, again, you will have the vector field F will radiate outward on the surfaces of S1. If I continue this, for example, I get another smaller box, it will again have positive divergence. Every point will have positive divergence, and thus the flux will be positive, meaning that the vector field F on the surfaces will again radiate outward. Doing this until it is very close to S, we will see that if I remove all the boxes from the point P naught, you will have the values of F will somewhat radiate outwards. This type of phenomenon is what we call a source. And that is, if the divergence of a point of F at a point P is positive, that is called a source. Otherwise, we will call it a sink if it is negative. And the reason why we call it source and sink is because in fluid mechanics, it is seen that if the divergence of at a point is positive, then the fluid will expand about that point. If it is negative, it will contract like a sink. And if it is zero, we will call the flow incompressible. And the reason why is because the divergence of F is equal to the negative rate of change of the density. So if the divergence is zero, then the density will be zero. The change of density will be zero as well. And that means you are neither expanding nor contracting, and that's why we call it incompressible. Divergence of F equal to zero is a very important assumption, especially when we study fluid flow. And you will see this type of assumption, especially when you study partial differential equations. Now, these types of behavior can be seen through the following examples. If f of xyz is just this vector field, then you will see that the divergence will be always positive because you have a positive x squared plus y squared here. If it is this constant, then it will be zero. And if it is the negative of our first example, you will have a negative divergence. And you will see when the divergence is always positive, the vectors seem to diverge or they seem to expand. While if it is negative, they seem to converge or they seem to contract. And that's the name divergence, because true enough, the divergence somewhat describe the way the vectors of the vector field behave, whether they diverge if it is positive or whether they converge if it is negative. Now we will be concluding our topic for Gauss Theorem by studying the result of Gauss Theorem in 2 dimensions. As you may know, since Gauss's theorem requires 3 variables because it has a triple integral that is indicated on the right-hand side of our equality. For us to define Gauss theorem in 2 dimensions, we first need to make a notion of a flux in 2 dimensions. And that is the flux of a fluid in R squared of the velocity field F across a piecewise smooth curve C will be given as follows. Be careful. We have a lot of line integrals that in our topics of Math 23. This is a line integral of a scalar field. The scalar field here is f dot n, and this is with respect to the arc length S. So the flux is given by the line integral of f dot n across C with respect to the arc length S. And here is the unit normal vector of C. Now, Gauss's theorem in R squared will be as follows. Instead of having a closed and bounded solid G, we will have a closed and bounded region R. And instead of having a surface S, we will have the perimeter curve C, which is piecewise smooth. Also, the n here will be our unit normal vector in C. And it is stated that the flux of f across your curve C will be equal to the double integral of the divergence of f over the region R. We will see that in R squared, we reduce the dimensions of both sides. That is, instead of having a surface integral on the left, we only have a line integral. And instead of having a triple integral on the right, we only have a double integral. Of course, this is over the area A in comparison to the over the volume V on for Gauss's theorem in R3. Also, it is very important to note that we have the curve here should be closed and it should be positively oriented, as is indicated by the notation that we have here. Positive orientation is very important since if your curve is positively oriented, automatically the n will represent an outward normal vector, or that means that the normal vector will not point inward but definitely will point outward. Let's have an example. Before we have an example, I will place the formula again on the left side of the screen. So let's have this example. I want to find the flux of the fluid with the following velocity function across our unit circle. This is oriented counterclockwise so that we are dealing with this positively oriented curve. Now, to use Gauss's theorem, of course, we need to find the divergence. And clearly, the divergence of f will just be 3x squared plus 3y squared. If I let B to be our unit disk, then Gauss's theorem in R squared tells us that the flux is equal to the double integral of the divergence of f over our unit disk B. The divergence being x squared plus y squared with 3, so I can factor it out. And it is now left to show how to evaluate this. Since we are dealing with a unit disk, instead of using the standard rectangular coordinate system, I will use polar coordinate system. And that is dA will become r d theta, x squared plus y squared will be clearly r squared. We still have the 3, and since it is the whole unit disk, I will have 0 to 1 for my r and 0 to 2 pi for my theta. Evaluating this, we will obtain the answer of 3 pi over 2. Of course, this is much easier than evaluating all of the line integrals as we have done before. Now, if you observe it well, we have seen this notation before for positive oriented curve, and that is for Green's theorem. So I think it is good to be able to compare what's the difference between Gauss's theorem and Green's theorem. Let us put them side by side. For Gauss's theorem, I have the line integral of f dot n ds across my curve C to be equal to the double integral of my divergence. While for Green's theorem, I have the line integral of p dx plus q dy, which is equal to the double integral of qx minus py. Both of these equalities or theorems will involve a line integral equal to a double integral. They also talk about a positively oriented curve C and a double integral over the enclosed region R. Though they may look very different at first, but it can be proven that Green's theorem and Gauss's theorem are equivalent in R squared. And we can see that through the following illustration. For one, they have exactly the same requirements, and that is, if let f be equal to pq, pq, its components, should have continuous first partials. Let us have a parametrization for our curve C, where C is a simple, closed, piecewise, smooth, positively oriented curve. Of course, R will be the region bounded by C. To demonstrate that, we have the following. As I've said before, because C is positively oriented, my R, which is the tangent vector, will point in this form, and that will tell you that the normal vector will automatically point outward. Now, let C be the tangent vector. Let R prime be the tangent vector as given by x prime, y prime. And the unit normal to C will just be the normal vector here, which in this case will be y prime negative x prime over its norm, which is just y prime squared plus x prime squared. We're going to be doing this because to connect Gauss's and Green's, we need to first express this quantity here in terms of t, and then later on express it in terms of this form. So for ds, we will need to get the r prime and the n so that we can expand it, which is given by as follows. So we have the line integral of f dot n ds here. If I expand it by definition, f will just be pq. I'll get the dot product with the normal we have obtained before, times ds. Now, ds in terms of dt, if you recall, will just be the norm of r prime dt. And the norm of r prime dt is exactly x prime squared plus y prime squared, which is exactly the norm that we have in the denominator. If you cancel this out, you will obtain py prime minus qx prime dt from a to b. And since y prime dt is just dy and x prime dt is equal to dx, then this quantity will just be the negative q dx plus p dy over the curve C. It's very much similar to what we have right now for Green's theorem, where we have a dx dy. And thus, for this form, if I apply Gauss's theorem, it will become the divergence of f across the region, over the region R, and that will just be px plus qy over the region R. While for Green's, I cannot apply Green's theorem for something of this form, but since I know that this is equal to this, then that will be equal to, by Green's theorem, the one in dy will just be partial with respect to qix, minus the one in dx will be a partial with respect to y, which is a negative. So in this case, the one with respect to y, I will get its partial with respect to x, so I'll have a px. And the one with dx, I'll get the negative partial with respect to y, which will now become a plus qy, which is exactly the one that we have here. It really means that Green's and Gauss's theorems are equivalent in R squared. You just need to be careful on what form you're applying it. If it is on the first, you use Gauss. On the second, you use Green's theorem. And that ends our lecture on Gauss's theorem, as well as the end for the Math 23 lecture series. I hope you have learned well, not only for this lecture, but all the lectures beforehand. Thank you for watching, and I hope you are all safe.